What's going on, everybody? This is Johnny Bannon with Trepa Technologies, and we're starting our Network Plus N10-009 course, starting with Domain 1.1, which is going to be the OSI model. I have up there Domain 1.1.1. That's how we section it off in our course when you take our full self-paced training. So here's the objectives for Domain 1.1. Layer 1 is going to be the physical layer, Layer 2, data link, Layer 3, network, and we're going over the OSI model here. Layer 4, transport, Layer 5, session layer, Layer 6, presentation, and Layer 7, the application layer. So this whole subdomain in our network objective, Domain 1, is going to start off going to the OSI model. The OSI model really is the first place that we start troubleshooting, right? It's going to give us a guideline, kind of a framework for real-world troubleshooting. And as an engineer, day-to-day working, if you're working with users like a Tier 1 support, you got Tier 4 support, whether you're working on MPLS, traffic engineering tunnels, SD-WAN, something high level, or you're doing Layer 2 troubleshooting, Layer 1 troubleshooting with the user, the OSI model never goes away. So no matter what level you're at, and again, as you get into the real world, you do network engineering, cloud engineering, it becomes a little bit just more second nature to use the OSI model. But for the Network Plus course, these are our fundamentals. So we have to understand this, and we're going to deep dive and break down the OSI model. We're going to have a couple whiteboard sessions when we go over Layer 3, Layer 4, maybe some Layer 2. And that's just because as network engineers, we care about every layer. But really, we care about end-to-end connectivity, right? Now, obviously, we get into our firewalls. We're going to have to know what ports and protocols our application layers work at, right? But we're not programming. We're not creating a web application where we have to worry about layers 5, 7, and 6 as much as a network engineer, right? We care about packets reaching end-to-end. So with that being said, let's just go ahead and dive right into it and start learning the OSI model. So the OSI model was created in 1978 and was officially published by the ISO, the International Standards for Organization. And it's just a way to describe the different layers at which data communicates over any computer system. And the OSI model that we're going to talk about is going to be Ethernet-based, right? IP-based and TCP/IP model, of course. Because if we get into SCADA and OT, anyways, we look at the OSI model as also a way to describe data encapsulation and de-encapsulation. So you can see here, if we start from the user data, work our way down in the layers, we can see how from end to end, what happens when I send that email, right? That's essentially how I always look at the OSI model is when I'm actually going to the web browser, I go to facebook.com or youtube.com. The OSI model is a good way to describe how that's going to work. How from end to end, through the layers, how our data gets encapsulated and de-encapsulated. So this little chart here is a nice chart we use to describe or to kind of look at how our data gets encapsulated, right? We're going to go over this chart at the end of this PowerPoint presentation as well, but here's our OSI model. Here's all the layers. I kind of have over here just some like high level as a network engineer, what we need to know about. When we hear the words TCP, we're thinking Layer 4, Layer 5. We hear the words IP, that's Layer 3. We think of media, so that's our MAC addresses, and our Layer 1, our Cat5, Ethernet. We're thinking layers 1 and 2, right? TLS or SSL, the secure sockets layer. TLS obviously being the secure version of that, the upgraded, the enhanced version of that, right? The cipher suites that are not end of life and not vulnerable. That's the session layer, presentation layer. So again, just a quick overview here. So now diving right into one of our layers, let's go over Layer 1. So the physical layer. This is going to be what I like to call the first step in troubleshooting, right? There's also a Layer 0 that maybe we might get to called the user error layer. But anyways, Layer 1, that's going to be anything that connects your devices to the network. So let's think about that. That's our copper cable. That's fiber. That's also Wi-Fi, guys. That wireless RF signal that connects Wi-Fi enabled devices to the backbone area, to the distributed network. That is Layer 1. So we have a couple different standards of Layer 1 when we think about our enterprise, our campus network, our data centers. So obviously we have copper and we have our twisted pair, unshielded or shielded twisted pair. If you ever made Cat5 before, and hopefully you have, if you ever made it to a knock, hopefully you got your lickings down there at the bottom, right, making cable. And don't worry, even double CCIEs and senior network engineers working in data centers, they still make cables sometimes, right? So that's kind of the standard. It's what we're used to, right? A user at home, Spectrum, wherever the local ISP comes in, they connect the modem to an access point, wireless router. They use Cat5, Ethernet, which is shielded or unshielded twisted pair. We have a couple different standards, as you can see here. We have Ethernet, fast Ethernet, gigabit Ethernet. And of course, we have things higher, 10 gigabit, 40 gigabit, when we get into our ISP, our data center networks. And we have different standards in how we actually create those RJ45Ns, right? So at layer 1, we go over copper. We're talking unshielded and shielded twisted pair. We have different standards in there called Cat5, Cat5e, Cat6, Cat7, Cat8 that are going to give us different speed, throughput, and bandwidth standards. And then shielded twisted pair is going to protect us from things like EMI, right? Because it has that little tin foil wrapped around our twisted pairs. Unshielded twisted pair gives us no protection from any like physical interference. And there's obviously going to be a cost difference there. And then we look down here at different cabling standards of how we actually terminate that RJ45 end. So we're going to have something called the T568 Alpha and T568 Bravo standards. Down here in my little diagram, this is the T568 Bravo standards, okay? Where it's orange, white, orange, green, white, blue, blue, white, green, and then brown, white, brown. And if you have ever made an RJ45N, you'll know what I'm talking about when we look at those twisted pairs, okay? Beyond just unshielded and shielded twisted pair, we have coax cable, which is still used, right? That's what brings your like broadband connection into the house sometimes, right? If you don't have fiber, it's that coax cable. And then we have fiber, another layer 1 technology or in the physical realm, right? We have two modes in fiber, multi-mode and single mode. With single mode, it's going to be used for a long distance. We're talking kilometer distances. Undersea cable, right? That's spanning the whole world, continent to continent. Obviously, those are a little bit more robust than the single mode you're going to see in like a little data center. But essentially, the difference between single mode and multi-mode is the distance, the bandwidth, and throughput as well. Single mode's for that long distance. You can see why here. With single mode, you have a single laser going through that single smaller glass core. So you're going to get less, I guess maybe attenuation you'd call it. It's kind of more for like electrical signals. You get a farther distance with it. Because with multi-mode, you have that bigger glass core that's bouncing, right? Where you have laser or light bouncing through that glass core. So you don't get as much distance on it. And then, of course, Wi-Fi. Wi-Fi as the just signal, that RF 2.45 and now 6 gigahertz signal that radiates from the antennas from your access points, that's also layer 1. Because that's going to send data, do signal channeling from device to device. So that's also going to be layer 1. Okay, layer 2, that's going to be our data link layer. When you think layer 2, think MAC addresses. And when you think about a physical device that does layer 2, think switches. Side note, layer 1, if you think another physical device is a hub, just a little tidbit in there. A hub is layer 1. Layer 2, think switches, right? Layer 2 is our data link layer, and this is going to be all about MAC addresses, okay? So the function, it's responsible for node-to-node data transfer and error detection and correction. It also manages MAC addressing and flow control. Just a way to say that this is our Ethernet standard, right? The data link layer is our Ethernet standard that's going to have that link sub layer and then that media access control layer. A switch is a layer 2 device that will forward what we call frames. So at layer 2, when we're forwarding data, we call it frames. And then those switches at layer 2 are going to make forwarding decisions based off their MAC address table, sometimes referred to as a content addressable memory table. And what you see on the screen here is actually a Cisco Catalyst switch. I worked in Cisco shops and data centers and enterprises. So Cisco CLI around here is what I'm used to. And of course now they're SDN solutions. Anyways, that show command you see here is a MAC address table. That's the brain of the switch. That MAC address table is what differentiates it really from a hub, where it's logical, where it's going to forward based off destination MAC address, and it's going to build the MAC address table based off ingress or source MAC address, okay? So let's go to our whiteboard here and look at layer 2. Okay, so we're going to draw out, let's see, our switch here, and we're going to label this layer 2 forwarding. So here's our switch. And this switch is going to have what's called a MAC address table. This is going to be our MAC table. Okay, and in that MAC address table, we're going to have things like VLANs, right? But we're going to have the port and then the actual MAC address that it learned on. And I'm not going to draw out what a real MAC address table would look like, just for brevity reasons, right? But essentially, you're going to have what port that MAC address is on, and then the actual MAC address. And again, that MAC address is going to be a 12 hexadecimal number. I'm trying to make my handwriting better. 12 hexadecimal digit number. Hexadecimal, if you don't know, is going to be 0 through 9 and A through F, okay? So it's going to be 12 hexadecimal digits or numbers. And, you know, a number is not actually accurate. Let me put digits there because we have letters as well, right? So it's not just numbers. Now, let's say this is switch 1 here. And let's say switch 1 has a device connected to it. This is going to be PCA. And then this is going to be PCB. And these PCs are all going to have their own MAC addresses. So we're going to say this PC's MAC address is going to be AA. This PC's MAC address is going to be BB. Now, of course, when we first plug in and we boot up, the switch is going to learn that MAC address and it's going to build that MAC address table. It's going to have that ingress, okay? But what do I mean by that? How does this MAC address table actually get built? Well, when PCA wants to communicate on our LAN here, because let's say this is a local area network, right? On our network here, it's going to build a frame, and that frame is going to have a layer 2 header. So in that layer 2 header, here's what it's going to look like. So let's say this is our layer 2 header, and then we have our data here, right? And actually, let me move this down a little bit because I want to make my data look a little bit better. Make it a little longer, right? A little bit more accurate there. So we have our data payload. And typically that's going to be 1500 bytes. We'll get to that, right? Bytes. And then at the trailer, at the tail end, we have a FCS, a frame check sequence. Let me draw that. FCS. Okay. So in that layer 2 header, though, we're going to have the source MAC address and the destination MAC address. So in our scenario here, if PCA wants to talk to PCB, and this is assuming that these two devices have already communicated prior, here's how the MAC address table gets built. I know it's like chicken before the egg, and I'll explain this, right? Essentially what I'm describing here is known, let me write this out. Known MAC address forwarding. Okay? So let's say this is gig 0/1. This is gig 0/2. So 0/1, 0/2. So when I create this layer 2 header, again, my source MAC address, and let's say I'm PCA. This is PCA's frame. I want to talk to PCB. That's BB. When I send that frame to the switch, it's going to look at that source MAC address, the ingress, and say, oh, hey, MAC address AA is on port 01. And let's say PCB is already communicated, so that's already happened. Now that it's going to build that MAC address table and say, hey, I just got a frame on my gig 01 port. The ingress, the source MAC address was AA. So I'm going to build that MAC address table. And now let me inspect the destination MAC address, that layer 2 header. That device wants to talk to BB. Well, I know BB lives on port 02. So now I'm going to switch that frame out 02. And that's how we do known MAC address forwarding, okay? If this was unknown, I don't want to break this down too much, but this is unknown MAC address where we didn't know where BB was. We would do something called frame flooding, where we change that destination MAC address to all F's, the broadcast MAC, and forward it out all ports besides the one it came in on, okay? But this is layer 2 forwarding in a nutshell, right? That MAC address table is also built off CPU in most cases, right? Like in Cisco devices, that's going to become important if we ever talk about network security in the Network Plus exam. But this is layer 2, guys. MAC addresses, switching, and frames. Now let's go back to the PowerPoint. Okay, now moving on, let's go over the network layer. So the network layer is going to be all IP based, okay? So this is going to be part of the TCP/IP protocol suite, right? The IP address is that unique address that a device is going to have when communicating on a network or in a computer system, right? In a computing network system. I like to use very open language. This is a CompTIA exam, so I don't want to Cisco-fy this. But anyways, layer 3, right? It's all IP addressing. So this could be a multi-layer switch. This could be a router that's building global routing tables. Talk about BGP, global routing tables, the internet, right? Or we're just talking router tables and like our integrated service routers, our small business routers, even the routers at home. This is how we forward packets, okay? This is how we forward packets outside our LAN, and we forward based on the destination IP address. So layer 3 devices make forwarding decisions based on the best IP route in the routing table. And what we mean by that is, hey, if I'm communicating to Facebook.com, obviously there's some things in the background, DNS, hostname to IP address resolution. But now I'm building a layer 3 header, and my destination IP is going to be to wherever I'm trying to get to. Well, my router is going to look at that destination IP, look at its routing table. On the screen here is another Cisco's routing table, and say, hey, do I have a destination to there? Okay, I do. Let me forward it out that outgoing interface, or whatever that next top IP address is, which would still be, at the end of the day, in that data plane, the outgoing interface. Anyways, so again, layer 3, the network layer, that's going to be IP addressing, and that's going to be devices making forwarding decisions based on the best IP route in the routing table. Now we have the transport layer. So layer 4, this is going to ensure reliable data transfer between host systems. It's going to manage flow control, error checking, and data segmentation. And the layer 4 protocols we need to know about are TCP and UDP. So, okay, guys, brief, just high-level overview. TCP, that provides us reliable data transmission. Now, you may be saying, well, don't we send based off IP? And you're correct. But IP, the internet protocol, whether it's version 4, version 6, does not let you know if all your data made it or not. It's just sending. That's just like, hey, I know the mailing address. But you won't be able to verify if your package got there or not just based off having the mailing address, right? That's like IP address. The transport layer, TCP, or when you get to UDP, TCP is a reliable way to ensure that all of our data made it from source to destination, whether that's client, server, it doesn't matter, right? Source to destination. And with that, TCP, it's one-to-one. So that is unicast communication, and it uses something called a three-way handshake to establish that data channel that's going to allow us to ensure that all of our data made it there. Now, with that TCP three-way handshake, we have some things called TCP window scaling. When you download something, you can see how it gets faster, right? Sometimes TCP limits you on your full bandwidth and throughput utilization because it's ensuring that all the packets make it there, right? So it's doing that, it's making sure that all the packets get there. Now, UDP, we call this a best effort protocol because it doesn't ensure reliable communication. Now, you may be saying to me, well, why? Why would we ever use that then? Well, there is a place for it, and you use it every single day, especially if you stream or watch any video online, or if you ever talk in the cell phone. That's UDP, right? UDP sends. It's going to send, and it's not going to worry about and restart your data channel and restart the transmission of data if there's a few packet loss. And that's what you want, right? Because imagine you're streaming 4K and you have some packet loss, which is totally possible because 4K, that takes a lot of bandwidth, takes a lot of data to create that 4K stream. Well, if we were using TCP on that video stream and we lost a single packet, a single bit, a single byte, some bytes, it'd restart that whole session over again. With UDP, we don't want that. When we're talking on our cell phones and we're driving 80 miles an hour down the highway and we transition from cell tower to cell tower, we don't want to lose that. We don't want to drop that phone call. So UDP is the layer 4 transport protocol. It's just going to send. Now, with UDP and IPv4, right, we have one-to-one communication, we have one-to-all communication, and one-to-many communication. So that's one-to-one is going to be unicast, that one-to-all is going to be broadcast, and the one-to-many is going to be multicast. And broadcast and multicast is always going to be UDP-based. It could also be unicast, though, as well, right? With TCP, again, because it's reliable, it's always going to be one-to-one. It's always going to be sender to receiver, source to destination, client to server, right? It's going to have that client to server architecture with it. So with that being said, let's hop over to our whiteboard again and talk about that three-way handshake. Okay, so let me zoom out here and let's, one second, there we go. And let's zoom out and come over here and let's talk about layer 4, our transport layer. And yes, this whiteboard will be available for you guys watching this course on YouTube or wherever you're watching it on our self-paced course. These whiteboards will be available to you. So layer 4, the transport layer, specifically, let's go over TCP and the three-way handshake. Okay, so what we're going to have here is we're going to have the client and we're going to have the server. So this is going to be source and destination. This is going to be sender and receiver, however you want to call it, right? I'm going to call this client and I'm going to call this server. Because when we're thinking about the TCP three-way handshake, I mean, we're thinking about, at least for me, if I go to a blog, if I go to YouTube, if I go to Facebook.com, TCP connection to a web server out there in the ether somewhere, this is what I'm thinking of, right? Client to server architecture, one-to-one communication. This is TCP. So what happens? So once I connect to a website as the client, I'm going to send what's called a SYN. So I'm going to build my packet now. It's going to be layer 2 header, my layer 3 header, and now my layer 4 header, TCP. And there's going to be port numbers assigned to this. So if I'm going to this server via HTTP, destination port's going to be port 80, right? And then my source port may be a ephemeral port. Especially we get into network architecture, right? Network plus class, doing that. It's going to become important. But anyways, so in that layer 4 header, the TCP header, we're going to have what's called these TCP flags. These flags are going to initiate sessions, they're going to acknowledge sessions, they're going to end sessions, and they're going to make sure that our data channel that's built after this three-way handshake is still receiving all the packets without any packet loss in our TCP data transmissions. So this client's going to send what's called a SYN flag. So that's step 1. Step 1 is send a SYN flag over to this server. The server is going to receive that, and it's going to say, okay, this client's trying to initiate a TCP session with me. That's what the SYN flag is, right? Let's start a session. So the server is going to acknowledge that, but then also start its own session with the client. So the next step, step 2, is going to be send a SYN and an acknowledgement flag from the receiver or the server. The client's going to get that acknowledgement and say, okay, it got my SYN, but now it just sent me a SYN flag, so it wants to talk to me as well. So as the client, I'm going to send back now just an acknowledgement. Once we do that, and you see 1, 2, 3, the three-way handshake. Once we do that, the client and server are now going to establish a data channel. And let's just say, for example, the protocol we're using here is HTTP, and we're downloading something via HTTP, right? The Hypertext Transfer Protocol. So we're going to establish that pipe right here. We got our data channel now, right? Okay. Data channel. And now we're going to start downloading and uploading things from this client into the server. Well, one thing that's going to happen is going to be something called TCP window scaling. I'm just be TCP scaling here. So what we're talking about is, right, let's say this is just 1 second here, and then this is 5 megabits, right, 10 megabits, 15 megabits. Well, as that client, let's say, is downloading something from that server, that data channel is going to increment us up. And we're using our SYN and ACK flags to acknowledge that our 1500 byte packets, if that's what our maximum transmission unit is, are getting end-to-end without any fragmentation, interference, or any loss, right? So let's say the client here is downloading, we're getting 5 megs, 6, 7, 8, 10 megs, and then we notice packet loss there. What TCP is going to do for us is it's going to scale us back down and then come back up, okay? And this is something called TCP window scaling, where we start reaching a threshold, essentially. We start losing packets, and TCP says, let's scale you back down, okay? Now, there's obviously WAN optimization solutions out there that's going to say, hey, we noticed that you keep having packet loss at, let's say, 8 megabits per second. We're going to cap you there. We're not going to let you go higher, right? We have some WAN optimization solutions for that, okay? Now, this could be in the form of like F5s. You know, we use something in my enterprises called Riverbeds that do this on a scale for a large enterprise and ISP. But that is the TCP three-way handshake, okay, in a nutshell. Now, we can expand on this, right? When we add in TLS to this, when we talk about like SYN, like network security, right? How you can have SYN flood attacks. But in a nutshell, this is the TCP three-way handshake. Now let's go back to our layers, our OSI model, and let's go over layer 5, 6, and 7. And I won't be as in-depth here. The reason being, just because, you know, we're network engineers. I wanted to really dive deep into layers 1 through 4, and now we can go over the additional layers that we still have to be concerned about as a, you know, contributing member of the IT operations team, right? So layer 5 is going to be our session layer. So the function, it's going to establish, manage, and terminate sessions between two communicating devices. It controls the dialogue between devices. So some key concepts. So we have session establishment, the process of creating a communication session between two devices. It does synchronization. It ensures that data streams are properly synchronized. It does checkpointing as well. So this allows the session to resume from a certain point if there was a disruption without having to start over. This is like TLS, right? This is like us getting on our web browser and, you know, doing a request and getting a response. So real world scenarios, video conferencing. The session layer is responsible for setting up and managing that stream or that session. It ensures that the video and auto streams remain in sync. And if they ever get out of sync, your session's messing up, right? You may have some errors. You may have some interference there. The presentation layer. So the presentation layer is going to communicate, obviously, between layer 5 and layer 7, the application layer. And it's going to do data encoding. It's going to do data compression. And it's also going to be doing encryption and decryption. So at the presentation layer, we're taking what we would see as like plain text, right? Regular numbers and letters as we would see them in our human alphabet. And it's converting that over to binary. It's also going to allow us to do data compression. So that's taking a file maybe from 4 megabits to 2 megabits. And then the presentation layer is also going to be able to do the encryption and decryption. SSL, right? This is that secure sockets layer that will be changing our plain text into ciphertext on our data in use, or our data in transit. Okay, and then we have our application layer. So this is going to be the user, right? What the user sees. So this is when you get on Microsoft Teams and you send that instant message, that's that application. When you go on your web browser and you go to google.com, that's using HTTP or HTTPS, the hypertext transfer protocol, to access that website. When you're sending emails using your Outlook, that's using the simple mail transfer protocol. These is the application layer, right? What the user sees. And now just to cap it all off, let's take a look at our OSI model again. And now this may make a little bit more sense from a high level, right? Layer 7, the application layer, that's the end user. Layer 6, that's the encoded, encryption, and compressed data. The session layer, that's how we're going to manage connections between endpoints, your sockets, right? And that's like the, bringing TCP into it. With when you add that layer 4 header, you call your data packet a socket, right? That's also going to be things like APIs, where you're getting access to databases and things like that with your application programmable interfaces. And then, of course, the layers that I am most concerned about as a network engineer. And again, that's not saying don't forget the upper layers. No, of course, we have to, if we're managing firewalls, know about HTTP. And if we need to allow it, if we need to allow DNS protocols through, right? But the core of our work as network engineers, network admins, is going to be layer 4 and down. That's the transport layer, TCP and UDP. The network layer, that's IP addressing. That's a router. That's packets. Layer 2, that's our data link layer. That's going to be when we're talking about our layer 2 switching, our MAC address, what we call frames. And then, of course, never forget about layer 1. It's going to be our physical layer, right? That's going to be our copper, shielded twisted pair. What you would just commonly say Cat5, right? Single mode, multi-mode fiber. Hubs, that's a device that's layer 1. And then also Wi-Fi signals. They are also layer 1. Okay, now let's go ahead and do our quiz. So I'm on our learning management system, and let's go ahead and do a quick quiz just to make sure that we do a nice check on learning for everything we just learned about. So question 1, if you were troubleshooting a problem where devices on the same local network could not communicate with each other, which OSI layer would you likely begin with? Okay, so this says, would you likely begin with? I'm going to go with the data link, the physical layer. Okay, sorry, I just got a little distracted there. Yeah. So where would you likely begin with, right? This is a good question. I try to mess you up with that local network there. So the physical layer, right? That's where all troubleshooting begins as a network engineer. So the physical layer is where we're going to start when we begin troubleshooting our local network, okay? That tripped me up because it said local networks. I thought LAN, and then anyways. So that's actually a good question. We want to begin with the physical layer. And here you can see our learning management system here gives us a nice explanation when we get things wrong, which is awesome. Okay, question 2. In which layer of the OSI model does the process of session management, including the establishment, maintenance, and termination of connections, occur? That is going to be our session layer. So as you can see here, the session layer is responsible for managing sessions between applications. Question 3. Which layer of the OSI model is responsible for determining the path that data will take from the source to destination across multiple networks? So I'm going to go with the network layer. That's IP addressing, right? That's our router looking at the routing table and saying, oh, you're trying to reach here? Well, to reach this destination prefix or network, go out this exit interface. Question 4. Which layer of the OSI model is responsible for translating data formats and handling encryption and decryption to ensure that data is in a usable format? That's going to be our presentation layer. So again, that's going to be doing that's going to act as a translator between the application layer and the network. It's going to be responsible for that data translation, conversion, right? Doing encryption, doing compression as well. Question 5. Which OSI layer is primarily concerned with ensuring that data is transmitted error-free and in the correct sequence between devices? So that's going to be the transport layer. So that's TCP, right? things like the transmission control protocol with that three-way handshake that makes sure things aren't fragmented. We don't have any packet loss. Then final question, at which layer of the OSI model would you find devices such as switches and techniques like MAC address filtering? Well, like we've talked about, layer 2, the data link layer, that's all switching and MAC addressing. Awesome. Let's view our results. We got one right, one wrong there. That's my bad. I just threw myself for a loop. Sorry, this video is a little long. But awesome. So that is domain 1.1, explain concepts related to the OSI reference model. Thank you for viewing, and check out our next video.